and today I want to talk a little bit about why we built them, how they work, how you can use them, and kind of where the future is. My name is Michael. I've been working with Neo4j for 8 years now, and kind of part of the inventory there. So basically, what graph algorithms give us is insight into structure. So we have a lot of data that we get from all over the world, lots of different sources, and we can analyze this data kind of in the local space. So by doing a graph pattern query, like we've seen before, where we kind of look at the neighborhood of a certain node, but we want to basically also be able to analyze the whole structure of the graph and take this information to get more insights. And so I want to talk a little bit about that, and then look at why does graph analytics work now so well? Didn't work so well before, and then we want to look how you would run such a pipeline and what the graph algorithms are meant for. I hope I find enough time for the demo. I have a bunch of demos. Basically, there are different things that you can get from analyzing graphs. So one is that you can look at what information flows through a network. For instance, if you have an energy distribution network or another distribution network, traffic and so on, and what happens if you interrupt this network at certain points. What are the crucial points in this network? For instance, if you if a power station shuts down, that's not a critical path, then large parts of your network can go dark because then you kind of destroy the critical path. The same is true for traffic. All of you that have spent time in traffic jams know that oftentimes it's just one junction that keeps all the traffic kind of back. And then if you resolve that, then everything is okay again. And so these kind of individual points in the network can have a lot of impact in congestion, failure, and so on. Other things that you can get from path analysis is, for instance, efficiency in routing. So for internet protocols, but also for other flows of information, for flows of money, and also other things like energy and so on. You also want to have alternative ways. You want to have the most efficient way, the most cost-efficient way to get data from A to B. And there you also have to analyze a lot of parallel paths to find the most efficient ones. Things like shortest path search, routing, navigation in general is something else. And then the other thing that's really interesting is that we can, just by looking at the structure of graphs, we can already infer a lot of the global structure. We can also infer a lot of the local structure. So how many communities or clusters do exist in the past? Who connects clusters? Who's influential in a cluster? So I can see, for instance, all the people that are interested in a certain topic, and whom would I have to talk to, for instance, to spread an idea within this group. Or if I have people living in a country and they are forming also clusters because you have urbanization and so on, and there's, for instance, a disease spreading in this country. Where do I have to look for instance, to stop this disease from spreading by vaccinating the right kind of people, for instance, and then kind of stopping the epidemic in its initial point. The same is true for information flow. So who are the influencers in networks? And as we've seen with the US election, for instance, and also other elections, that you can, by placing kind of influential bot networks in the right places, you can influence outcomes of political decisions pretty easily today. So there's a lot of stuff that we can learn from graphs in general. Why does graph analytics take off now? The animations are a bit too much. I didn't do them. Because we have now the compute power available. So one aspect is that we have now the data available. So we can get data from many different data sources. We can combine data sources. We can bring things together. So one example is the Panama Papers data set, where the journalists of the ICIJ got the information from the leaks from the law firms that create shell companies, but then they augmented this data with sanction lists, census information, company registries, ownership information, property ownership, and kind of by bringing all these networks together, they got a much completer picture of reality, more or less, right? And that allows them to do these observations. And on the other hand, you have also the compute infrastructure now available. Now at a swipe of your credit card, you can command like thousands or tens of thousands of CPUs and exabytes of RAM, more or less, at your proposal. No. And so you can also use all this compute capacity to work with this data. And the two things coming together kind of made it possible that we now can do these kind of analytics much easier. We saw from Jerry how easy it is, for instance, with Spark to just grab the data, put it on Spark, on a Spark cluster, and compute it, for instance, something like the Bitcoin. Okay. We can get a lot of insights from graph algorithms. I already mentioned things like failure points, structures, and so on. But we can also do things, for instance, we can enrich networks for better recommendations. So by understanding human behavior patterns, so who did what in the past, but also how things are related to each other at larger scale. How do I do kind of compute similarities between large intersections of items in a retail store, or of movies, or of videos? Things like Netflix created their micro-categories for movies from like analyzing viewer behavior and analyzing on the other side kind of content information about movies that they had. And this is all possible by kind of taking all this data, the structure, and running algorithms on top of that. Basically, classical graph algorithms give you things like metrics. So what are centralities of nodes? So what's important? What's the influence of a node? What are clusters that we can find? What are other structural insights that we can get? But then on top of that, we can also apply machine learning on graphs. So we can extract embeddings for each node. So that means a node with a certain structural environment and their properties can form an embedding for a machine learning algorithm as an input. And then we can use that as well to not just classify and predict information, but also use the deep learning algorithms to detect, for instance, structures that are at higher levels that we want to see. So you can use, for instance, things like convolutional networks to also find structures in graph structures and not just in images. So that's kind of really interesting aspects. Something else that's really interesting is that actually all the neural networks that you use in deep learning are actually graphs. So they are kind of neurons connected with edges with weights. So you can also kind of put them into a graph or graph database or in graph analytics system to get more insight of how does this neural network actually work, what are actually influencing aspects, which parts kind of participate in how in decision making and so on. So that's pretty amazing. So that's something that we're currently looking into. The right side, and graph algorithms is something that we've already been working on. Structures can hide in the graph. One example that I really liked a lot is Game of Thrones. Andrew Beveridge, a mathematician from California, took all the Game of Thrones books, so all the 5 books that we have right now, because Winds of Winter is not coming out yet, right? And analyzed character interaction. So he looked at a book text and looked at which characters appeared within 15 words of each other. So that was either one character talking about the other character, 2 characters interacting, or one character killing another character, and what you do usually, right? And so he found in total more than 7,000 interactions of characters, and put them all into an interaction network, and then just ran some graph algorithms on that. And basically, what these graph algorithms do is they get the same kind of insight that you get from reading the books. So when I read the books, then I know, for instance, that Tyrion is very influential because he's kind of involved with a lot of people and kind of doing all like his intrigues and so on. But the graph algorithm also gets the same kind of insight. So they, if you look at, for instance, things like PageRank or so, then where's it? Here, John has a high PageRank, and Tyrion has the highest PageRank. So he's the kind of most influential person in this kind of interaction graph, right? So which I also know because I've read the books, but you know, a stupid graph algorithm who kind of can't understand the books and they are like literally content can come to the same conclusion. And that was quite an impressive thing for me to see. How do you run graph algorithms? So in the past there were already many ways of running graph algorithms on Spark with GraphX or graph frames, on Apache Flink, on Giraffe, on Turi, there's Hadoop from Martin. the Boost library, and so on. So there are many ways of running iGraph, many ways of running graph algorithms. But what we from Neo4j wanted actually for people using Neo4j is that they don't have so many moving parts, so that they can just take the data that they already have in their graph and just run graph algorithms on top of that without having the additional things to do. So what we also wanted to avoid is kind of to transfer data. So for instance, the Bitcoin graph that Jerry showed before, I wanted to copy the data from one machine to another, and it was like these 600 gigs of data took like over 8 hours to copy over the network. So if I transfer these large amounts of data over a network which is kind of not fast enough, then it also takes some time to do all the data transfer. And scalability is more an issue with classical tools like iGraph in Python or in R, where they are bound to a single machine and a single CPU, and that is sometimes also a problem. So we had an example from a partner company of ours called Right Relevance. They did Twitter analytics on the US elections and Brexit data, and also on other data like Ebola data and so on. And they ran a pipeline like this. So they ingested got the tweets from the Twitter streaming API, put it first in MongoDB, then moved them over to Neo4j, and then did some querying and aggregations in Neo4j, but then they also exported the data to R, ran certain algorithms in R and iGraph, and then they took some of the data, wrote it back to Neo4j, and had like a cycle of iterating there, and then they used MySQL to put the data into Tableau and exported it into GraphML to get it into Gephi. So it's kind of the whole shebang of things that you can have, right? So it's like a hodgepodge of things. And so we were talking with them, and they said we really would like to simplify this pipeline and make it easier and remove lots of these kind of additional parts that we don't really need. We just needed them because the capabilities were not there. And so we looked at it and we said, okay, actually, if you talk to us anyway, then we can also kind of remove these things, right? So because you can access Twitter streaming API directly from Neo4j and put the tweets directly into the graph. With the new graph algorithms, we don't need the iGraph stuff in R anymore. There's a Tableau connector for Neo4j, and there's also direct Gephi integration for Neo4j. So actually, if you already want to focus on Neo4j as your data store, then you can do all of these things without the other moving parts. And the thing that was kind of missing back then was the graph algorithms, and that's something that we worked on since. So what can we do in terms of graph analysis in Neo4j? Originally, Neo4j is a transactional database, so meaning it's meant for transactional workloads. So you can build like a retail system with that, or an ordering system, or a hotel reservation system, or something like that, where you have lots of small transactions going through the system, lots of reads, lots of writes, but not like large-scale analysis. That was not kind of the focus of Neo4j before. But you could already do some analysis by using Cypher and just running Cypher over your graph data, for instance, to compute something like degrees, or compute small clusters and stuff like that. But it was not really efficient. What we added as an additional capability to Neo4j was that we can implement now user-defined procedures and functions. So that means you can write your own code, which then becomes callable from Cypher. So you can keep your regular Cypher statement, but at a certain point you want to, for instance, do something custom business logic, or you want to run an algorithm, or you want to do a special conversion, or you want to reach out to another database to pull in some additional data. And that's kind of really easy to do with these additional procedures, which we then also use as the approach to implement the graph algorithms. So all the graph algorithms that I will show you are also implemented as user-defined procedures, so you can just call them from your Cypher statement. That means you can have an already existing Cypher statement that computes certain aspects, and then you just pass parts of these results into the graph algorithms procedures, and then they can use that. And with the results that come out of the graph algorithm procedure, you can also, again, reach into your graph and pull, for instance, additional information for these nodes and relationships. And all of that runs on Neo4j, so you don't have to leave like Neo4j's process, but it's all running in process for Neo4j, which is kind of really nice. And not just on a single node, so we can also run these graph algorithms on dedicated compute nodes in a Neo4j cluster. So if you have like a regular cluster that runs your transactional workload, then you can also add a bunch of machines that are larger sized and run as like reporting or compute instances, and then you can run these graph algorithms on these machines. So far we implemented algorithms from 3 areas. We did centrality algorithms, community detection, and pathfinding algorithms. Basically, you use them like you use every other user-defined procedure in Neo4j. You can call them with the call syntax, and then each algorithm has a name, so a prefix with algo, then the algorithm name, and then we have 2 variants. One has a stream suffix, which means it gives you the data back to your query. So imagine you run a PageRank, then you get all the nodes and their score back to your query, which is okay for medium-sized graphs, but if you stream back like a billion nodes to the consumer, then it's pretty hard to handle that kind of on the fly. And that's why we also have a second variant, which doesn't have the stream suffix, which just writes the data back to the graph. So each node, for instance, would get their score directly written to as a property, which is quite convenient because then you have it materialized in the graph, and then you can, for instance, also use these scores in your regular graph queries as well. So for instance, if I computed already centralities, then I can also just use them in my next query, for instance, to find what are relevant people or what are relevant products or relevant movies that have a higher centrality score than other ones, and can use that to improve, for instance, the quality of recommendations. So that's the basic approach, and as parameters you pass in optionally a label that you want to have, or a type, a relationship type, and then some additional configuration depending on the algorithms. For instance, something like dampening factor or iterations or weight information and so on. And that's one aspect. And the other thing is that we also want to have these projections. So if you were here for Yuri's talk, he said that he actually had to create 2 separate graphs, one for the whole Bitcoin data model and one that had only transaction to transaction information, so like a bipartite graph. And what we can do in these algorithms, that instead of passing in here labels and relationship types, we can also pass in one cipher statement that creates a node list, one cipher statement that creates an edge list, and then it uses this virtual graph to run the computation. So you can take any graph data that you have already in your graph and just project it to whatever you want to have, right? So for instance, you have a Twitter graph with users, tweets, hashtags, and all this other stuff, and mentions and retweets and replies. And for instance, you want only to have the user-to-user mention graph, right? Then you just write here, find me all the users, and then find me a user who posted a tweet, which mentions another user, and return user 1 and user 2, and then perhaps the frequency as well. And then you have a virtual projected graph, which then the algorithm is run on. And so you can project your graph into any shape that you need or want to have for running these algorithms. Okay, so what did we implement? We implemented, in terms of centralities, PageRank as a baseline algorithm. Between the centrality, closeness centrality, degree centrality was already there in Neo4j out of the box. Harmonic centrality as well. And we are also looking into some other ones. And here's an example for PageRank on Dbpedia. So we can just run PageRank on Dbpedia, stream the results, and pass in label and relationship type, and then return just the top 20 nodes from Dbpedia. And the same I can do with writing the data back, and then I can pass in a write property, where I can also say I have different properties that I want to write to. For instance, I can say I want to run PageRank for this subset of my graph and write to property A, and I want to run PageRank for this other subset for my graph and write it to property B. And then I get this statistics information back. How long did it take to compute the data? How long did it take to write back the data to Neo4j? So for community detection, we have currently label propagation, unified, so weakly connected component, strongly connected components, Louvain, and we also added triangle counting, which is not really a community detection algorithm, which was quite interesting. And things that we want to look into going forward is something like walktrap and infomap as higher quality community detection algorithms. And here are examples again. So these examples look similar, but in the demo section we see than kind of how they work in detail. And for pathfinding, we have a single source shortest path, all nodes, single source shortest path, multi-source breadth first search, and then also in general parallel breadth first search and depth first search implementations that are mostly used by the other algorithms as an infrastructural thing, but also exposed in the library itself. And there's also Dijkstra implemented and as a parallel Dijkstra as well. Okay, here's, for instance, an example where I find a starting node and find all the single source shortest paths and write the properties back to the relationships in between. So what allows us to have these algorithms available, we can, as I said before, we can combine lots of different data sources into one graph, run our compute, we can project the existing graph to certain subgraphs, and enrich the data that we get with additional algorithms. And then we can use this to run queries on top. Okay, cool. Demo time. Let's see. So first of all, when you use Neo4j Desktop, then it's quite easy to install these algorithms. So basically the graph algorithm library, I have links in the end, is an open source library which is on GitHub. And network runs. So you can find it on GitHub. Documentation is also there, and also the releases. So you can also just grab the job for the algorithm and put it into your Neo4j server as a plugin. Or if you are running Neo4j Desktop, you can also just click on the plugins tab and then install graph algorithms here with a single click as well. So it downloads the correct version of the graph algorithms, adjusts the config, and puts the jar into your folder. So if I look here on my plugins folder, it has APOC and graph algorithms installed. Okay, and this is the Game of Thrones graph, so I can actually look at the Neo4j browser for this graph. And so first of all, when we look at this data, we just see our characters. What's wrong here with my computer? Demo gods. What? Let's try this again. Ah, there you go. So this is kind of a small subset of these nodes. Here's Cersei Lannister with a bunch of other people, and here you see that we have different, I can also make this bigger, different interacts relationships. So we have, for each of the books, you have a different interacts relationship, so we can also kind of discern the different things from the different books. And so you see here we have interacts 1, 2, 3, and 4 and 5. So the books 4 and 5 were actually only one book, but George R. R. Martin split it into 2. So what we can also do is we can just see how big is the graph, of course. Make it low. So it's 800 nodes and 3,000 something relationships, I think, 3,800 relationships. So we can also look at like degrees, so we can just find all the characters and then return just the size of the BPN. Just the size of the nodes as degree, and so these are the nodes with the top 5 degrees. Let's perhaps return the name. So this is kind of the degree centrality which Cypher can already do out of the box, so there's nothing that we have to do in particular. So but if we take this network now and want to run some of the graph algorithms on top of that. Or what I first can run is APOC nodes. Oops. Is the degree nodes? damn it, degree distribution. So we can start running algorithms on top of that. So you can look at this degree distribution first and see what's kind of our minimum maximum degree of 148. It's maximum degree, and then average is 6.5 with a standard deviation of 14. And now we can run algorithms on top of that. What's wrong here? So here in this case we run the PageRank algorithm. And we run the stream version, so that's the version that returns the data to us directly. And we get back the node and its score, and we want to have, for the top 5 nodes, we get the node name back and the degree of the node as well. So and it runs PageRank over the whole graph and gives us the stuff back. So we get Tyrion Lannister, Stannis Baratheon, Tywin Lannister have the highest PageRank over all the books, and that's their degree. And so we see even as Theon Greyjoy has a higher first level degree, its PageRank is lower. So because not so many people are connected to Theon Greyjoy as, for instance, to Tyrion Lannister, also in the second. As to Tywin Lannister in the second degree. We can also use that to write the data back to the graph, so that's actually pretty simple. So where we can just call algo.pagerank, which runs PageRank on our graph with 20 iterations and writes this data back to the PageRank property. So from now on, I can also just give me the character, the ones that have a PageRank, because some of them also don't get one, and then so and now I have these properties directly on my nodes and can use them for further scoring, for instance. So similarly, we can compute betweenness centrality. So here we take just the betweenness centrality between characters from the first book, and then find a character, and because you get just the node ID back. And here we see, for instance, that betweenness centrality is a metric that is high for nodes that connect clusters of other nodes. So, for instance, Eddard Stark is someone who connected many of the different groups in the first book, right? Because after the first book, Eddard was not anymore. The same is true for Jon Snow and also for Robb Stark in the first book, and Robert Baratheon. And Tyrion was actually very limited in terms of interaction. So in the first book, he was only in the group of the Lannisters. This changes later, where he becomes more involved. We could actually look in the books 4 and 5 if Tyrion has a better betweenness centrality. No, Stannis is still there, really high, and Jaime, interestingly, and Daenerys. Okay, what else can we do? We can run clustering on this. And here I wanted to show you how you do the cipher projection. So I just do the first statement, which returns characters as node list, and then the second statement is all the interactions, and we have just 2 characters, and we can here sum the weights of the relationships. So each of the relationships in the interaction graph has a weight, which is the frequency of interactions, and we can also use that for computing the communities, so in this case with label propagation, and we write it to a community property here. So we can just run this on this graph, so it runs in a few milliseconds, and then we can, for instance, look at the communities and their sizes. So the query here finds all characters that have a community property and then counts groups them by community. So we see we have some larger communities with more than 100, 150, and then it kind of goes down really quickly to small communities of a few people. And if you look at one of these communities, actually, so for instance, I had here the one with community 124, somewhere down here, with only 8 people. I want to see who's actually in this community. And if you look at the graph, then we see that. Something that I didn't want to see. So this is record. Oh, that's not what I wanted to show actually. Anyway, I think there's something that I ran before. So we can do the same with Louvain. And instead here we write to the Louvain property. And let's see if this works now. And here we get the same community sizes again. Do you see that Louvain is more evenly distributed? And here we can, for instance, this should actually be a network of Queen Circe. Yeah, so here we see Circe in the middle and all the people that we know from her interactions, like Baron Trent and the Cleganes are in here, and where's he? The other Lannister, Lancel Lannister, and so all the people around Queen Circe are in this cluster around her. So you can really identify, if you have read the books and you know the story, then you actually know kind of all these clusters that you see here in these in these clusters are actually making sense for you. That's actually quite cool. Okay, cool. Here's an example for the projected Twitter graph that I mentioned before. So I have Twitter users, and here's a mention graph. So a Twitter user to another Twitter user via a mention in a tweet, and then we can just compute, for instance, PageRank on top of this virtual graph, which we just projected. My next example is Dbpedia. So I mentioned before, so Dbpedia is a data set of 11 million nodes and 116 million pages, links between pages. And we can just run some algorithms on top of that. And if my network works, let's see. Doesn't look like it. So let's see. Come on, do it. It worked all the time while I was watching the other talks. It's just not working when I'm doing my own talk. But I'm getting funny characters in an SSH connection. Anyway, that's a little bit frustrating. But I think I have it here as well, yeah. So to run PageRank on this graph with 11 million nodes and 117 million or 60 million relationships takes 20 seconds, which is kind of nice, with 20 iterations. And union find runs, I think, in 40 seconds or so on Dbpedia. So clustering on Dbpedia, which is kind of a copy of Wikipedia pages with all their links between each other, which is kind of nice. And if you run something like PageRank and get the results back by ranking, then we see that pages like United States, Animal, France, list of sovereign states, these kind of listings pages are always really high up in the PageRank because they have a lot of links pointing to them, because it says, you know, all these people are, all these states are sovereign states. Germany shows also up. Here's another projection example. For instance, if you only want to have pages where there's Europe in the title and run only on PageRank between these pages that are just a subset of my graph, then I can do this as well. And this is my edge node list and my edge list, and then we can run this. I would love to show it to you, but it seems that the network is not liking me at all. Okay, so be it. Okay, so we can do also funny stuff. So on the clustering in Dbpedia, what we can also do is, if you run something like a centrality, like PageRank first and then a clustering algorithm, we can also use the centrality score to find the nodes of the cluster that are like the central nodes globally, but in the different clusters. So for each cluster, we can also find the node with the highest PageRank, for instance, and return this as this is the most influential node globally in this cluster, for instance. So we can also see how these are distributed across the clusters, and then also visualize that in Neo4j itself. We also did some Bitcoin analysis. Not as much as Jiri, but I got some cool inspirations from this talk, so I will definitely do some more. So Greg Walker is someone who runs a Neo4j graph. It's on a site that's called Learn Me a Bitcoin, and he continuously imports all the Bitcoin transactions that come along into the Neo4j graph. So currently, this graph has 1.7 billion nodes and 2.7 billion relationships. So it's 240 million transactions, 280 million addresses, and 650 million outputs. 600 gigabytes on disk right now. So the data model is a little bit hard to see here. So we have a transaction in the middle, which is linked to a block. And then each block has inputs and outputs. Where's the output? Where's the input? Can't see the input. So here's the output. The output is pointing or locked to an address. The input is also locked to an address. And then there's also the Coinbase as a starting point for the blocks. And something that I ran first on this large graph was to do a degree distribution for the locked relationship. And something that was really weird for me, at least, was to see that actually, although we have like 650 million locked relationships in this graph, like the 99.9 percentile only has 28 lock relationships. So the degree distribution of this relationship is super tiny. And then there are a bunch that have like 18 million or 1.8 million locked relationships. And Greg explained it to me because I'm a Bitcoin noob, so I don't know these things. And he told me, actually, people usually in Bitcoin, when they transfer money, they create every time new addresses, so they're not traceable. So you wouldn't send kind of multiple transactions with like the same address, with the same wallet address. And that's why most of these addresses have only one transaction or so originating from it. So you can't trace them kind of via multiple transactions. And the addresses with these 1.8 million, in most cases, are either payment addresses where like someone posted publicly a payment address, or ransomware. So if you do ransomware, you also have to post your Bitcoin address so people can pay you, right? And so that's actually something that you can find and trace really well in Bitcoin graphs. These kind of all ransomware payments, and you get like a lot of payments coming in, and you can follow the flow of information. So on the Bitcoin graph, on the 600 gigabyte graph, this ran in 300 seconds. And then as the next thing, I wanted to see kind of this kind of address-to-address virtual network. So kind of looking at which addresses send which what amounts to other addresses. So I ran a projected graph again, so with output and logs. So you see this data model is a bit more fine-grained than the one that Jiri used. And then I do the same on the edge list as well. I find these logs, the first 10 million, I think, is it? And so these are my two addresses, so address 1 and address 2. And then I just run the algorithm on that. And on these 10 million nodes, it runs in 300 seconds a clustering algorithm. So we see that there are certain clusters which have a lot of members, like 4.4 million or something like that. Yeah, 4.4 million members, so a really large cluster of people exchanging money, but then there are also a number of smaller clusters here that come out of that. So this was some experiments that I did on the Bitcoin graph about the implementation of the graph algorithms. Let's see. Basically, we wanted them to be really easy to use. So that means whenever I can write a cipher statement, I also want to be able to run my graph algorithm. So that's why we added them as user-defined procedures. So you can just call them from your cipher, and there's no extra tooling or infrastructure or anything that you have to set up. We didn't want to have data transfer. Could you close the door or come? Because it's really loud outside. We didn't want to have data transfer. We wanted to run these algorithms in the Neo4j process, which is still live running transactions. So it's not like that we stopped the Neo4j instance to run the algorithms on, but we can say, okay, use the concurrency of X, which is the percentage of your total number of CPUs, and the rest of the Neo4j database continues to run transactional workload at the same time while it's also running the graph algorithms. We wanted to parallelize everything, so make use of all the CPUs that we have available. So both the loading in data structures, computation, and writing back. And we also used a lot of like low-level Neo4j APIs to access the low-level data in Neo4j really efficiently. And of course, we wanted to scale to billions of nodes and relationships and using hundreds of CPUs and terabytes of RAM easily with these algorithms. And basically, the architecture is like this. So here is our algorithm implementation. We are accessing Neo4j in parallel to get the data into our data structures, run the algorithm in parallel, and write the results back to Neo4j. And as you can see, for instance, this is an HTOP from a machine with 144 CPUs, which runs PageRank, and they're all pretty busy, so that's kind of nice. So we really utilize our CPUs really well. And something that I actually was surprised by, because I didn't expect that, is that it actually performs quite well if you compare it to the published data, for instance, from Spark's GraphX. So for the Twitter 2010 dataset, which is 1.5 billion relationships and 40 million nodes, it's about in the same order of magnitude as GraphX. So the blue one is GraphX and the green one is Neo4j. So I expected it to be like an order of magnitude slower, but what we built, but actually we're a little bit faster, so it's kind of nice. And so mission accomplished in this space. Something that we started with initially was to limit these graph algorithms to 2 billion nodes and 2 billion relationships, so that we can use integers everywhere, which makes it much faster to build and use less memory. But now we are rewriting them to use long IDs, so we can run to arbitrary sizes. So here's an example of an 300 million node and 18 billion node graph that has 600 gigs on disk, and PageRank with 20 iterations on one machine with 20 threads runs in 1 hour 47, which is pretty good. And the same for triangle counting on this machine with the same 18 billion relationship graph runs in 3 hours 40 minutes, which is also quite nice. So I was quite happy about these results, and the new implementation that we have for the large graphs is even more memory efficient than the old one, because we do data compression of numeric integer arrays and do segments and stuff like that. So it's pretty nice. And I'm looking forward, so we are currently migrating all the other algorithms as well to the huge implementation, and then are looking forward to test this all out and report these results back. So this is kind of the scale that our customers want us to build for. So they wanted to have like up to tens of billions of nodes and hundreds of billions of relationships, and that's something that we are now working on to make this work. So it's mostly like large payment networks and people with lots of user transactions. So sites that have like hundreds of millions of users and they want to run their stuff. So all this stuff is out there and available, so you can just grab it. It's on GitHub. You can try it out with Neo4j Desktop or install it into your Neo4j server. We'd love to get feedback, so if you try it out, we'd love to hear from you. If it worked for you, were there any things that you would like to have different? Are there certain algorithms that you would like to see? Are there things in terms of usability that should be different or better? And so from that perspective, there are also a bunch of other examples where people wrote blog posts about using these graph algorithms on other data sets. So Tomasz Bratanek did it with Game of Thrones extensively and with the Yelp dataset from Kaggle. My colleague Will did it on the Russian Twitter trolls that have been published by NBC, and the US Congress ran graph algorithms on top of that. And then we also have it, we ran it also on Paradise Papers and Panama Papers as well. And I want to do more about the Bitcoin analysis. That will be a lot of fun. Okay, cool. I didn't do much of that except for starting the whole effort and then nudging people to do stuff. All the implementation was done by Paul and Martin from Dresden, from Avantgarde Labs, which was really cool. And Tomasz worked a lot on the docs, and my colleague Mark is taking the project over now for me and runs it from now on. And actually, he released just yesterday a new release of the draft algorithms, which have a new of the larger scale algorithms implemented, and it's available now on GitHub and Maven as well. Okay, and with that, I'm done, even in time. Any questions from you?
I've seen the last result that you had some algorithms that run over multiple hours. Do you have any way of monitoring that over time to see the progression of the
Yeah, so the question was, is there any way of monitoring the progression of algorithms? So the algorithms output progress into Neo4j's log files. So if you look at the log files, you see where the algorithm is, if they're currently loading or writing or executing, and also all the threads are outputting that. We're also thinking about exposing that, for instance, via monitoring tools, so you can also access it via monitoring, or even try to make it work so that the algorithm actually outputs like cipher records, and then kind of via streaming you would see like the records appearing one by one, but I have to first try out if it actually works across all the different layers of the stack to see that. Any other